As you know, random experiments such as coin toss can be executed multiple times. Today, we'll show you how you can work out the probabilities with the so-called tree diagram. So today, we're talking about tree diagrams in probability theory. You can represent every random experiment as a tree. Let's take the coin toss first. We say that we're tossing a coin 2 times. At the first toss, there are of course 2 possibilities, one being heads and one being tails. The illustration shows us our 2 possible outcomes for the first toss. If one of the 2 possibilities occurs, the coin is tossed a second time. For us, this means that the same trees are simply slapped onto the ends of the 2 outcomes again. A tip for later: the sum of the probabilities of a toss must always equal 1. So in this case, 0.5 plus 0.5 gives us 1. Here also, and here as well. Now let's calculate the probability of the first toss being heads and the second toss being tails. So that would be this path here. To work out the probability of a path, you just have to multiply the probabilities of the individual branches. So, the first path rule, the probability of a path is equal to the product of the probabilities along the path. For us then, the following applies. 0.5 times 0.5 gives us a probability of 0.25 or 1/4. Where there is a first path rule, there will also be a second. We ask ourselves the question, how high is the probability of getting 1 head and 1 tail each in 2 tosses? So here we have 2 distinct possibilities. We can get heads first and then tails, or tails first and then heads. An important hint to help you with the sum rule. If you can connect the probabilities with an OR, we apply the second path rule. In our case, reading as first tails, then heads, or first heads, then tails. The probability for the first path, that being heads first, then tails, is 0.25. This goes for the second path too, that being first tails, then heads, giving you a probability of 0.25. Now for the second path rule. The probability of an event is the same as the sum of the probabilities of all paths that lead to this event. So that means we add up our 2 probabilities of 0.25 each, which gives us a total probability of 0.5. Let's have a look at another example. We roll a dice twice, wanting to roll a 3 on the first roll and a 6 on the second roll. Each number of dots on the cube has a probability of 1/6. So our tree diagram will look like this for the first roll. Each number therefore has a 1/6 chance to be rolled. In order to keep things clear, we're only writing that on the first path, but remember that it applies to all of them. And to keep the whole thing clear this time around as well, we will only be drawing you the paths for the second roll for 3 dots. Again, all the probabilities here are 1/6 each. Now all we have to do is observe our chosen path. So, we take our path rule for the probability that the first roll will be a 3 and the second roll a 6, giving us 1/36 after multiplying the individual branches. Nice or what? So, what are the points to remember? Broadly speaking, every random experiment can be represented in a tree diagram. It is important to note that the sum of all the probabilities of an event is always 1. For example, when tossing a coin, the probability of either heads or tails equals 1/2 each, which together make 1. The first path rule states that the probability of a path is equal to the product of the probabilities along that path. The second path rule states that the probability of an event is the same as the sum of the probabilities of all paths that lead to this event. Remember that and you'll find everything much easier. If you want to see how things continue in probability theory, then you should probably stick around. Until then, bye-bye!